Consider the set U, which is made up of the elements A, B, C, D, E, F, G, and H. Next, let's consider the set A, which is made up of elements B, C, and F. Now, as a quick review to our previous lessons, one of the things that we reviewed is the cardinality of a set, which is the number of elements in the set. So as a quick review, calculate what is N of A, the cardinal number of A, or the number of elements of A. What is N of U? I recommend you pause the video now, answer these two questions, and then unpause to check your work. So as there's 1, 2, 3, 4, 5, 6, 7, 8 different unique elements in the set U, the cardinal number of U is 8. There's 3 elements in the set A, the cardinal number of A is 3. Another thing to note about, we've identified the cardinal numbers of both sets, but there's a bit more going on to these two particular sets as well if we start looking element-wise. For instance, notice B is in set A, and B is also an element of U. C is in set A, C is also an element of U. F is in set A, and F is also an element of U. So in this particular example with these two sets, we've been able to show that every element of the smaller set A is an element of our larger set U. And this particular idea of when every element of one set belongs in another set is the idea of subset. So when every element of set A is also an element of set U, we say that A is a subset of U. And the notation that we're going to use to write this, if we want to express A as a subset of U, we would write that as A subset symbol U. And if we wanted to express the idea that something was not a subset, all we would do is we would draw a line through the subset symbol, and this means now not a subset. So we have two new symbols that we want to commit to memory so that when we see them, we know exactly what they represent. If you see this symbol, you should think of it as is a subset of. Something will come before, that's the thing that's the subset of the larger set. And then the negation of that, not a subset. So let's go through a few examples. We will write either is a subset or is not a subset in each of these statements in order to make them true. Let's look at our first one. We have the set whose elements are 2, 4, 6 on the left, and the set whose elements are 2, 4, 6, 8, 13 on the right. So let's assess whether we could apply the subset relationship here. Remember, something is a subset if every element in the one set belongs in the other. So let's check. 2 is in the smaller set. 2 is also in the bigger set. 4 is in the smaller set. 4 is in the bigger set. 6 is in the smaller set. 6 is in the bigger set. Since every element here is an element of the bigger set, we would correctly write is a subset. Now I'd encourage you to pause the video and attempt this example. Begin by checking is every element in the first set part of the second set. If that's true, then subset applies. If even one thing fails, then it's not a subset. So here as I look, A is in this set, but if you look through all the elements here, A does not belong in the second set. So since they disagree on any elements, we would use not subset. Looking at our next one, 30 is an element of the smaller set. 30 is not present here, so this one is also not a subset. Now take a moment to think about this last one. I encourage you to pause the video, attempt it on your own, really think about what these ... means in terms of what is this set on the right. And whenever you've had time to think about it, unpause to check your work. We've seen this ... before. What that means is the pattern that set continues as expected, and since nothing comes after it, it continues out forever. So what is the pattern? 2, 4, 6, 8. It looks like we're going up by 2 each time, so the next pattern would be 10, 12, 14, 16, and that's just going to continue on forever. So the set on the right is actually all the positive even numbers greater than or equal to 2. So let's think about this. 6 is in the smaller set. 6 is present in the other. 12 is in the smaller set. 12 is present in the other. 24 is in this set. And even though I didn't write it out, 24 will come later in this set because it's going to keep going up by 2s each time. So the next element would be 18, 20, 22, 24, 26, and so on. So we know that even though it's not expressly written out, it is definitely a member of this set because it tells us the pattern continues. So this is a subset because every element in the left belongs in the set to the right. Let's consider the set U, which is A, B, C, D. So for the set U, is it true that it's a subset of itself? And whenever we're asked these kind of mathematical questions, we always go back to the definition, because it's not kind of a what do you think is the answer, it's what is a definition and do we meet the definition. So looking back, the definition of subset is every element of this set must belong to this set in order to be a subset. So let's just check element-wise. A is an element of the first set. It's also an element of the second set. B is an element of the first set. It's also an element of the second set. C is an element of the first set. It's an element of the second one. Same with D. So every element here is an element of the other set that we're looking at. So by this very definition, they are definitely subsets of each other. And this is just what's going to follow directly from the definition. Every set is a subset of itself, because if you look at it, every element in the set is definitely in itself, so it meets our definition of subset. Generalizing from this discussion, we could always say that every set is a subset of itself. So no matter what set we're looking at, if we were looking at set B, I could correctly make the statement that B is a subset of itself. So keep this idea in mind. Every set is a subset of itself. So we've learned the definition of what makes one set a subset of another. Let's refine this definition and talk about the idea of proper subsets. Consider the two sets, D, which is made up of the elements 2, 5, 8, and 10. Set A, which is made up of the elements -4, 2, 5, 8, and 10. Let's verify this statement. So remember, as we're reading mathematical notation, we read left to right. So it says set D. This is the symbol for subset. This is set A, so this would be phrased in English as D is a subset of A. Now, in order to check whether something is a subset, we go element-wise. We look at the first set mentioned, which is here, and we check is each of its elements present in the second set mentioned. So let's just verify that briefly. 2 is in set D. It also appears in A. 5 is in D. It appears in A. 8 is in D. It appears in A. 10 is in D. It appears in A. So definitely D is truly a subset of A. But between the sets D and A, we can actually be more specific. Not only is D a subset of A, but we could clearly say that D is not equal to A. And the reason D is not equal to A is A has this additional element, -4. And if y'all recall from previous lessons, we learned that two sets are only equal if every element in one set is an element in the other set. But as -4 is in A but not in D, we could say that set D does not equal set A. So when we can make the following two statements, when it is true that something is a subset of A, so if D is a subset of A, and it's also true that D is not equal to A, these two things bring us to make the more specific statement that D is a proper subset of A. And this is written in mathematical notation as D proper subset A. The distinction between a regular subset and a proper subset notation-wise, regular subsets have the subset symbol and then the kind of horizontal bar below. So I always think of this as it's a subset and it may be equal. We're not being specific. Whereas in a proper subset, as it's missing that bottom bar, this is telling you that it's a subset and they're definitely not equal, because that's part of the definition. In order to be a proper subset, you have to be a regular subset, and the two things cannot be equal. So adding this to our list of definitions and notations that we want to commit to memory, the set A is said to be a proper subset of set B if A is a regular subset of B and A is not equal to B. So we have to check two things before we say something's a proper subset. The notation that we would use to write this is A is a proper subset of B. So based on what we know so far about subsets and proper subsets, which statement do you think gives more specific information about set relations? Which one's going to mean more if you see it written on a page? Proper subset or regular subset? Take a moment and pause the video to think about it. If needed, I encourage you to go back to our definitions, review those, and then think which of these two symbols gives more information. The proper subset gives more information because a proper subset tells us not only is something a subset, but it also meets the additional criteria that the two things are not equal. So as proper subsets include being a subset itself as part of the definition, we could say that all proper subsets are actually regular subsets. But since they have this additional criteria of not being equal to, proper subsets are a refinement on the idea of subset. So it is true that every proper subset is a subset. However, there are subsets that are not proper subsets. So that's how we're going to think about which statement is a stronger statement. Proper subset is stronger because it includes extra information that they're subsets and not equal. Now in this next example, we're going to look at the statement written and we're going to assess whether we could correctly include the symbol for subset, proper subset, both, or neither. And if you're ever asked to check, should you put a subset symbol or proper subset symbol, the procedure is always to check, is it a regular subset first? Because if it's not a regular subset, it can't be a proper subset. If it is a regular subset, then you check the additional thing, are the two things not equal? Because if it's a regular subset and it's not equal, then by definition, it's a proper subset. So this will kind of be the flow chart of logic that we're going to go through to these type of problems. First step, check if it's a regular subset. What we do there is, if we recall, we just checked element-wise. 2 is in the smaller set. It's also in the bigger set. 4 is in the smaller set. It's in the bigger set. 6 is in the smaller set. It's in the bigger set. So far, we check yes here. So we answer the next question. Are the two sets equal? At a quick glance, the second set has elements 0 and 8, which are not present in the first set. So these two sets are not equal. So they are not equal, which means our conclusion is it's both a subset and a proper subset. Because the whole definition of proper subset is that it's a subset where the sets are not equal. So here, both statements would make it true. It's true that it's a subset, and it's true that it's a proper subset. Similarly, go through this example, check with the flowchart, pause the video, and unpause when you're ready to check your work. So we first begin by asking, is it a regular subset? We do that element-wise. 3 is in this set. It's also in this one. 5 is here, here, 15, 15, 18, 18. So it is a regular subset, so we go to the next question in our flowchart. Are the two sets equal? To see if two sets are equal, remember you just check is everything in one in the other, and is everything in the other one in the first. 3 is here, 5 is here, 15 is here, 18 is here. So everything in the first set is in the second, and everything in the second is in the first. So in this case, these are equal. So our conclusion is, since they're equal, they are regular subsets, but they can't be proper subsets because proper subset has in the definition that they're not equal. So as these are equal, we're left with this conclusion. It's a subset, but not a proper subset. So as you do the homework problems that are related to this idea, you might write down this flowchart, and it can help you just sort through the logic of when something's a subset, when it's a proper subset, and when is it both. Let's let U be some set. We don't know what it is, it's just a general set. Based on our definition of subsets, we want to assess whether these are true or false statements. Now, do you remember what this symbol represents? So the 0 with the dash through it represents the empty set. And the empty set is the set that has no elements. It's empty. So the statement read left to right that we're trying to assess whether it's true or not is the empty set is a regular subset of U for any set U. Now keep in mind, we don't know anything about U. We don't know how many elements it has. U could be the empty set itself, or it could have one element, it could have 2 elements, it could have 100 elements, it could have infinitely many elements. U is just a general set. So let's check what is a definition of subset. It means every element here is also an element here. So what are the elements of the empty set? By definition, the empty set has no elements. So this is what we would call in mathematics a vacuously true statement. Since the empty set has no elements, it is true that every element here is an element here. Because there's no elements here, right? There's nothing to make it go wrong. So every element of the empty set, of which there are none, is an element of any set U. So because we've met the definition of subset, it is true that the empty set is a subset for any set, no matter what the set is. So there's a little bit of abstract reasoning. Now, if you would, read this out loud to yourself. What's the difference in notation between our first and our second statement? The difference is that the first statement uses regular subset, and the second statement uses the more restrictive proper subset. So for proper subset, not only does it have to be a subset, but the two things can't be equal. So think about if this is true or false. And I think it would be helpful to you as you're considering that to read the third statement as well. So pause the video, read these two, and think about it. So the second statement is the empty set is a proper subset of any set. The third statement says the empty set is a proper subset of any set, provided that the set is not the empty set. Our second statement would be false because we don't know that it's a proper subset of any set, because what if you happen to be the empty set? Then they would not be proper subsets because they're actually equal. Our third statement is true because it takes care of that one problem point. So long as the set U that you're looking at is not the empty set itself, then the empty set is a proper subset of U. So I'd encourage you to kind of wrestle with these ideas. This is about as abstract as we're going to get in this section, but it's just the idea that the empty set is a subset of any set, and the empty set is a proper subset of any set so long as the second set is not the empty set itself. So now that we've introduced the idea of subsets and proper subsets, let's think about the idea if I have a set, how many possible subsets could I construct of that set? So in this example, consider the set A, which is 2, 4, 6. What are all the possible subsets of A? And whenever we try to answer questions like this, what are all the possible things that could occur? We need to go about writing these down in an orderly fashion to make sure we don't miss anything. So to be a subset of A, it has to have some, if not all, of the elements of A itself. So since A only has 3 elements, 2, 4, 6, our largest subsets could also only have 3 elements. If I have more elements than A, it's not a subset because it's not living inside the original set. So in this example, I know the largest possible subset size would be a set with 3 elements. Now think about what's the smallest subset size? 0 elements, which is the empty set. So as we list it out, we're going to have our subsets with 0 elements. Then we'll list the subsets with 1 element. Then we'll list the subsets with 2 elements. Then 3 elements. And we know for this particular example, there's nothing past that because A only has 3 elements itself, and if I have more elements than the original set, I'm no longer a subset. So how many subsets have 0 elements? Only the empty set. Now, how many subsets of A have 1 element? Well, you could have the set that just has 2. You could have the set that just has 4. And you could have the set that just has 6. Now, in terms of the 2-element subsets, we need to think about all the possible mixtures of 2, 4, and 6 in groups of 2. To write that in an orderly way, let's start at 2. 2 could be paired with 4. 2 could also be paired with 6. And then that's all the possible pairings of 2 with other elements of A. So then we move forward and say, how could I pair 4 in ways I haven't already paired? Now, if I write 4 is paired with 2, that's actually the same thing that I already wrote, because order of the elements within the set does not matter, so I don't want to repeat myself. However, if we look, 4 has not been paired with 6. Okay, there's nothing else to pair 4 with that we haven't already done, so now we think about starting at 6, but 6 has already been paired with 4 and with 2, so there's nothing else that could be written there. So we move on to the 3-element subsets. And the only subset with 3 elements is the set A itself, 2, 4, 6. So how many possible subsets are there? 1, 2, 3, 4, 5, 6, 7, 8. And it does not matter that my elements were 2, 4, and 6. Any set that I started with that had 3 elements in it will have 8 possible subsets. I'd encourage you to take a moment to work through this next example in a similar way. Now we're restarting for the set with elements 2, 9. Write out all the possible subsets. So start with the smallest size of subset, 0 elements, that's the empty set. move up to subsets of one element, etc., until you reach the limit for this particular example. Pause and attempt on your own. Unpause to check the work. So as our set B only has two elements itself, the largest possible subset has two elements, which would be itself 2, 9. The smallest subset is the empty set always. The set with one element is the set 2, and the set 9 separately. The set with two elements is itself 2, 9. So for the original set that started off with two elements, there are 1, 2, 3, 4. Now the empty set, we know every set is a subset of itself, so the empty set is its own subset, so there's only one subset of the empty set itself. If a set has one element, then you always know it's a subset of itself and the empty set is a subset. So if a set has one element, it has two subsets. So let's organize what we've seen so far in a chart. So if a set originally has 0 elements, that would only be the empty set. The only possible subset is the empty set itself, so there's one possible subset. If a set has one element, then the possible subsets are the empty set and the set itself, in which case there's two possible subsets. As we saw earlier, when there's two elements, the possible subsets are the empty set, the first element set, the second element set, and then the set with both elements. So there's 4 possible subsets. And whenever there's 3 elements, the possible subsets are the empty set, the first element set, the second element set, the third element set, the first with the second, the first with the third, the second with the third, and then its set itself, which is 8 possible. Now, if we continued this line of reasoning and we wrote out all the possible subsets for a originally 4-element set, you would get there's 16 possible subsets. And if you continued the reasoning further, if you start with 5 elements, there's 32 subsets. And you keep going, and the pattern emerges that if you start with a set that has n elements, then the number of subsets of that set is 2 to the n, 2 to the number of elements as the exponent. And we see that pattern expressed here. So if the set starts with 0 elements, there will be one subset because there's 2 to the 0. If a set starts with 1 element, there will be 2 subsets because that's using the formula 2 to the first. If it starts off with 2 elements, then by the formula 2 squared is 4, there's 4 subsets. If it starts with 3 elements, then 2 cubed is 8, there's 8 possible subsets. If it starts with 4 elements, 2 to the 4th is 16, 16 possible subsets. Now let's take this one step further. This is the formula to find all possible numbers of subsets given the size of the original set. How many proper subsets would there then be? Well, think about what is the definition of proper subset. It's a regular subset that's not equal to the original. So let's look back at our previous examples. In this first example, think about of the 8 subsets I listed, how many of these are not proper subsets? So if we were talking about proper subsets, which would we get rid of? If we look back at our definition of proper subset, it's a subset but not equal to. The only one that's equal to the original set A is the largest one. So instead of being, there's 8 possible subsets, but there's only 7 proper subsets because we have to get rid of the largest subset. So it's like we just subtracted 1 from there. Let's see if that pattern holds for the 2-element set. When we only were looking at the set 2, 9, the 2-element set, which one of these 4 subsets is not proper? the largest one. It's not proper because it's equal to the original. So there's 3 proper subsets. And this pattern is always going to hold if you have all the subsets listed out, then the largest subset is not a proper one because it's the set itself. You're always going to subtract 1 from the number of total subsets. So if a set begins with n elements, the number of proper subsets is 2 to the n, which gets you all of the subsets, and then you subtract 1 because you get rid of the biggest subset, which is the set itself. So keep in mind these 2 important formulas. If you start with n elements in the set, the number of subsets is 2 raised to the n as an exponent. If you start with n elements in your set, the number of proper subsets is 2 to the n. Once you figure that out, you then subtract 1 from the number. So we'll apply this in our next example. So we have the set Y, which has elements A, B, T, and U. And we're asked what is the number of subsets and the number of proper subsets for Y. Notice we're not asked to list out the subsets and proper subsets. We could do that. We did that in the last few examples. We're just asked for the number, which means we can apply the formulas that we just learned. So what is the cardinal number of Y? How many elements are there in Y? 1, 2, 3, 4. So the formula for regular subsets is it's 2 to the number of elements. We have 4 elements here, so 2 to the 4th. So calculating that, 2 raised to the 4th power, 16. The number of proper subsets, the formula is 2 to the n, then minus 1. Well, there's 4 elements in our original set, so 2 to the 4th, then minus 1. We know from above 2 to the 4th is 16. Minus 1 is 15. So there's 15 proper subsets and 16 regular subsets. So that's it for this lesson. Be sure to work through the assigned homework problems, and if you have any questions, do reach out and I'll be happy to answer your questions.